testing. So what does that look like? This is automotive SPICE. SPICE is really it's really a quality system. You mentioned APQP earlier. Okay. SPICE is really part of a quality system for software development, and it really follows a V process where you're designing down here and you're testing going up this side, and every step along the way you're looking across the V as well to make sure that you're meeting your requirements. So for example, when you're first doing your initial customer requirements and doing your analysis, you've got to be looking over here at the other side going, well, what am I going to validate to? What's this vehicle going to be when I'm all done? I need to know that up front so I can do this efficiently. And then as you come down the V over here, when you're you do modeling, controls, model development, go through the auto code generation, come back up the other side here, where now you're doing software in the loop, hardware in the loop testing, which is really bench top testing, and then get into prototype vehicles and hardware vehicles. So I mentioned this real quickly. I'll actually use this a little bit later. But this is basically the modeling process that you would use, or the analysis using advanced powertrain analysis type tools that we would typically use. And this iterates. Okay, this will just go in a loop. So what that looks like, we're doing the analysis, we're doing the Simulink code, auto code generation, going through compilation, putting it into the hardware, calibrating that hardware, basically tuning all the variables for the specific car, and then going through and iterating till, at the end we go through a verification, validation phase till we actually produce the vehicle. So one of the things that everybody says is, all right, you get a vehicle and they look at it, it doesn't, well, how fast does this thing go? What's the top speed? What's the all-electric range? Those are kind of the three that they care about. Well, in this series hybrid here, so when we're decreasing the state of charge, we're taking energy out of the battery into the motor, we're recapturing, we're bringing the charge back up by recapturing energy from the motor back into the battery. And then at some point, we get into what we call the charge sustaining mode, where now the generator's kicked in and putting energy into the battery and driving that rear wheel, the rear wheels, and the state of charge kind of is maintained. So these are some of the first things we'd look at when we go into an analysis standpoint of a particular powertrain. And we say, okay, well, what's your 0 to 60 time? Everyone wants to know, okay, if I stomp on it, how fast do I get to 60? Okay, how fast do I get from 0 to 100 if I got to step on it and pass somebody? Or what's my top speed? So these are some of, and there's plenty others. Our powertrain specifications will be hundreds of lines long, but it seems like these are always the first three that people start with: all-electric range, power, acceleration. So I'm gonna skip this. This is just kind of a little more. I think I've said most of that. So if you look at just a real simple block diagram: engine, generator, motors, battery, your auxiliary loads, gearbox. One of the things that analysis and PSAT, for example, autonomy will help you do is really specify these various components, their efficiencies, their losses, so that you can mix and match components. And you have to understand the characteristics of those components so that you can put the system together to, at the end of the day, come up with a powertrain that's going to meet your efficiency needs, your fuel economy needs, and quite honestly, cost. I mean, cost is always a big driver for all of this. And these are just some of the things that affect those efficiencies. Things that, levers that we have as engineers to basically improve the efficiency of the vehicle. So it's all just part of the analysis that we do. Now, one of the things that's interesting on a PHEV, how many times have you seen, somebody says, well, I've got a PHEV, it goes, I can get 100 miles per gallon, or I get 120 miles per gallon, or 200 miles per gallon. Say, well, what does that mean? In an EV, it's pretty straightforward. There is no gas. But on a PHEV, people kind of game that system somewhat. So if somebody's talking to you about a PHEV, you always got to ask them, wonder what conditions are you saying, or assumptions you're using to say that you get that kind of fuel economy. Because, for example, if this green line represents 50 miles, let's say you've got an EV that'll go 50 miles on a charge, and you never drive more than 50 miles in a day, 25 to work, 25 back, you recharge it, theoretically never turn your generator on, you never use any gas, you're essentially getting infinite fuel economy, right? You're driving all those miles and using no gas. As soon as you go beyond 50, those next 10 miles, you need your gasoline engine. Well, now you've gone 60 miles, but only 10 of it is on gasoline. The first 50 were all electric, right? So when you do the math, say you come up with about 120 miles per gallon. That sounds great. What happens if you go, 70 or 80 or 100 miles? Well, now you drop down, you come down this curve fast. At some point, you become constrained by the fuel economy of the base engine. So when you hear these wild claims about the fuel economy that a PHEV will get, they're typically using this kind of analysis. Well, I went 52 miles and I'm getting 200 miles to the gallon. That sounds fantastic. Well, that's really it's a bit misleading. So it's just a little bit of a primer on, next cocktail party when somebody's talking about their PHEV, you can quiz them on that. Anyway. Okay, so the last topic I want to go through here is ensuring that new technology meets safety requirements and standards. And we've talked about a lot of things. Some of the primary safety considerations at the vehicle level are occupant protection for crash, braking systems, steering suspension, chassis systems, your supplemental restraint systems, your airbags, etc. High voltage electrical systems now with all the EVs, HEVs, they all have high voltage on them, so you got to be very concerned about that. I didn't put on here the battery management system. We talked about that yesterday, and I forget who showed the pictures of the laptops burning and all those sorts of things. Obviously, that's a big concern. What I want to talk to you about is something called torque security. And ISO 26262 is a standard that's out there that's become the industry standard, because in the old days when you step on the throttle, you got a mechanical linkage that opens up the throttle blade on the throttle, and off you go. Well, a lot of those systems are being replaced now by what we call by-wire systems. Okay, so you no longer have these tried and true mechanical systems. You now have electrical systems. Well, they can have their own issues. So how many times, what happens when a computer freezes? I mean, this happens to me at least once a week. You're looking at it, and all of a sudden it just stops. And you're pounding on the escape key, Control-Alt-Delete, nothing. So you're like, okay, I'm just going to hard reboot, I'm going to unplug it, and then you realize I've got a lithium-ion battery in my laptop, so unplugging it doesn't work. I got to actually pull the battery out, wait a few seconds, put it back in, okay, and then it comes back up and it's working just fine, like nothing happened, right? I mean, everyone here has experienced that, right? Or am I the only one? All right. So, and varying degrees of anxiety when that happens, depending on if you're late for a deliverable or whatever. So consider what takes place between your foot and the rear wheel of your car. You step on that throttle and that car goes. Well, you think about for a minute what's actually going on. There's a lot going on, and there's a lot of things that can go wrong. So when you request torque, you step on the throttle and somehow torque's delivered. Well, what's going on in the black box here? There's lots of hardware, lots of processors, lots of little computers, right, like my laptop, lots of microprocessors, thousands of lines of code being executed, and this is all happening. Well, you've got to make sure that that torque is secure. And I could call it torque security. Torque produces vehicle movement. You don't want any unintended acceleration. If you don't put your foot on the throttle, you don't want the car jumping, or if you just put it on a little bit, you don't want the car taking off on you. When you take your foot off the throttle or put it on the brakes, we all expect a certain amount of behavior from our car. And electronic controllers, especially now as we've electrified everything on the cars, hybrid vehicles, PHEVs, HEVs, it's just proliferating more and more. Electronic controllers, by-wire systems are prolific, and so it complicates the problem. And so what ISO 262 is, it's really an international standard that's really becoming the industry standard, and it's really a methodology for defining automotive hazards, including torque security. How do we address it? It establishes criteria then for thwarting those problems, or thwarting any of those hazards, okay, and so that they occur in an acceptable level. What's an acceptable level? We'll talk about that in a minute. And ISO also addresses both hardware and software. You can have hardware failures, whether it's a sensor or an actuator or even silicone in a chip. You can have software failures. You can have thousands of lines of code and there's bugs in them. You don't catch everything. In some weird condition where all the planets line up, something can happen, or you can just have a failure of a base piece of silicone or a chip within a controller. Not Infineon chips, but other guys' chips. And so microprocessors already employ watchdogs, if you will, microprocessor supervision. So that's kind of the key here. So we'll talk about that real quick. So the ISO 26262, it's really beyond, It's like I said, it's a top-down methodology for defining all this. And I'll just point to this here real quick, is that ASIL D is the toughest, most stringent level, automotive safety integrity level. This is a classification for such a thing as torque security. And what ASIL D means, and I got to go through this quickly here, is the probability of allowed failure is 10 to the minus 8. So the probability is 10 to the minus 8th is the probability of that failure occurring, which allows a failure every 11,000 years of continuous operation. And that sounds fantastic. It's now, if you're a high volume manufacturer, and you do the math, it can occur. This 10 to the minus eighth doesn't mean that a probability of failure will never occur. Because when you start making millions of vehicles, you do the math, and I didn't do it specifically because I don't want to scare anybody. Yes?
It's kind of hard to believe a standard like that. You'd think like if you weighted for various scenarios or for environments, and what you think yourself, well, where would they get a figure like that? Driving in a straight, flat road, or paved, or what are you talking about?
Well, it's really hours of operation, and when you look at all the different components as a system, you've got to have redundancy in there such that if this thing fails, I've got a redundant way such that it still can't cause me to have a problem, and I can save the vehicle. Well, you might not ever be able to figure this out, but it is based on a lot of science because there is, over the years, we do have a tremendous amount of knowledge about what the occurrence of failures are for various components. Okay? And there's going to be bugs in your software. So there's the bugs. They're going to pop up when you least expect it. Okay? I'll go through this real fast, but there's a concept phase, product development phase, there's a hardware phase, and a software development phase that ISO really focuses on. So last couple slides here then, there's a couple ways to essentially secure your torque. You supervise, let's say this is your hybrid control unit over here, that's basically taking the input from the pedal, and you got redundant sensors in the pedal. That's one of the first things you do. And you calculate what's called a diverse software. You calculate things in a diverse way. So you're calculating essentially the same thing in multiple different ways such that you don't have a common cause failure. You've got multiple inputs, calculate things differently such that the output of this, if one of them is wrong because you've had a RAM error, a ROM error, you've had something go wrong within that controller, or it just went plain crazy, went insane, and it can't be trusted, you've got another controller watching that saying, hey, this doesn't make sense, doesn't line up. So you have a torque command, send out a torque envelope, and then what we call a seed and key, or a challenge and response. So if this were your HCU, you could have another controller, say the inverter, watching it and just checking it all along, making sure that that torque command is reasonable. And you create a torque envelope. Here's your torque command, basically your throttle input. And you create an envelope around it that's always checking to make sure it doesn't go out of bounds. And if it goes out of bounds, that monitoring micro has the ability to put that vehicle into a safe state so that you don't have a runaway vehicle on the 405. We've heard some of that in the news over the last couple of years, and you just have, you can't have that. So that's what this is intended to thwart. Or the other way to do it is, in addition to that, we have what we call a seed and key response. It's kind of like the old, kids playing in the pool. You say Marco, and you hear back what? Polo, Marco, Polo, Marco, Polo. Yep, okay, everything's cool. If you said Marco and you heard nothing, or you heard something strange, then it's like, wait a minute, what? And then you do that a few times, say, hold on, something's wrong here. I'm sending the vehicle into a safe state. I don't want my torque to get out of control. Okay, so if the main is bad, it's caught by this seed and key response, monitor to detect the failure and force a safe state into the vehicle. The other way to do it is to essentially go through, have a monitoring micro within the same silicone, if you will. And for example, the semiconductor guys, such as Infineon, such as Freescale, they've really become partners in this. Instead of just spanking out components and saying string them together and you figure it out, they've actually worked within this process, within this specification, working with the automotive groups to develop architectures where you can have monitoring microprocessors on the same die, on the same silicone as the main, and so you can do all this within the same component as opposed to distributed across multiple components. And it's the same thing. The second core can detect that there's a problem. The main core has gone insane, can't be trusted. Take remedial action. Okay? So lastly then, future vehicles, I said before, we need less battery, not more battery. They need to be smaller, lighter, cheaper, all that good stuff. We need to decrease manufacturing costs through high volume automation to improve quality and repeatability. Okay? We also need to look at, and I think Mike talked about that yesterday, combining solutions that look at lithium-ion batteries and ultracaps. It's got to be considered for light-duty vehicles and heavy-duty vehicles. Advanced engineering tools continue to be important to be competitive and decrease time to market. And lastly, torque security. If something goes crazy, you've got to have a way to recognize that and not let that failure become a safety issue at the vehicle level. And any of you who have a chocolate lab might recognize that picture. Mine looks like that very often. Anyway, That's not my dog, but I recognize it. So anyway, that's it. Thank you.